into a little bit of linear algebra, because we have seen how to build a model and how to find, how to select the best model and how to do exploratory data analysis and all that, right? Now we want to know how exactly the algorithm is working. Is there any problems with the algorithm? Okay, because the way linear regression algorithm works is a little weird and it takes lots of space in memory. So when you are handling huge volumes of data, right, this algorithm may not fit well. So before we know the linear the mechanism, right, we should understand a little bit of math. So there is a diagonal matrix and identity matrix. You must be knowing it, right? Diagonal matrix means only diagonal values will be there and rest of the values are going to be zeros, like this. When diagonal values are ones, right, we call it as identity matrix, and when you multiply any matrix with identity matrix, you will get the same matrix. I think you know this, right? And then inverse of a matrix and singular matrix. We need to understand this. So on a square matrix, I am showing you inverse. If you take the bigger matrices, right, it becomes complex. We need to understand what it is. Okay, no need to be an expert in doing inverse of a matrix and all that. So if you have A, B, C, D, a matrix, if you want to find A inverse, we need to find 1 by AD minus BC into D minus B minus CA. So I have taken 8351 and then applied, calculated A inverse. Okay, this is the A inverse. So in this equation, this AD minus BC is called as AD minus BC is called as determinant. Okay, this is called as determinant. This part is called as determinant. For a matrix where the determinant is 0, we call that matrix as singular matrix. If you see this 5533, if you calculate AD minus BC, it is 0. Right? If you want to calculate inverse for this matrix, can we calculate that? Inverse is there for this matrix. Do we have an inverse?
No.
No,
Because
right? So
1 by 0 is infinite.
1 by 0 is undefined, right? So there is no inverse. A matrix that has no inverse is called a singular matrix. Okay, so we need to remember this. Symmetric matrix is like, upper triangular and lower triangular values are same. That is symmetric. Singular means no inverse. Okay? Determinant is 0. So this is singular matrix. See this value is equal, this value is equal. If you fold it, right, this by the diagonal, you will get the same triangle. Okay? That is, symmetric matrix. A inverse is A transpose is equal to A. Okay, so A inverse is equal to A is also there. No, A inverse is not. No, when you multiply two matrices, you get identity matrix. That is called the orthogonal matrix. You will see that in now the eigenvalue eigenvector decomposition. So when there is no inverse for a matrix, we call that as singular matrix. So let us try to understand how exactly the linear regression algorithm is finding theta in a single shot. I told you, I don't know whether you remember it or not. When you pass your data set, the algorithm will take its hypothesis function and form equations of the hypothesis function with the data you passed. Right? In our example, we have passed salary, designation, all the other fields, and designation, educational qualification, experience, all these features as X, and salary as Y. Right? Salary is Y. So when we passed it, it actually formed linear equations, straight line equations. Theta 0 into theta 1 into whatever value in the first record, theta 2 into whatever value in the second column, first record, second column, and so on is equal to y value for that person's salary. Let me show you that. So if you take this data for this first record, it will actually take some variable name associated, some variable name multiplying this value plus, anyway we'll convert it into numbers, at some variable multiplying this value, variable multiplying this value, variable multiplying plus 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 and so on is equal to salary. That's what we do, right? This salary, this target value. And the second equation also will form like that, third also, fourth also, like that. So if you have million records, right, we will form million equations and solve all of them at once. How is it solving? Using normal equation. This is the way. What is x here? All the input data in a matrix is x. All the input data in a matrix is x, and all the output data, the salary, in y. It's a one-dimensional. It's a column matrix. Okay. So m rows and one column. And if you substitute all x's and y in this equation, right, you will get thetas, all thetas, the coefficients. Got it? Any questions here? This is called as normal equation. Any questions here? So how is it actually finding these thetas and how this equation came in? Is a deep linear algebra. If you are interested, right, you can actually go into this.
There xt is the transpose of the matrix, sir?
Yes, sir. Yes, sir.
Okay, got it.
Linear algebra by Gilbert Stang. If you say, right, remember this person. Right, linear algebra by Gilbert Stang. Okay, he's a MIT professor and very nice, very nice linear algebra classes, but it takes a lot of time. Each video is around 47 minutes. So if we can spend time, that's definitely going to be good. Around 17th video, I think, is talking about the normal equation. 17th or 18th. I don't remember. Okay, but I watched it long back. No, if you are interested in how this equation is working, you can go to the Gilbert Stang's. No, he actually has a linear algebra book also written. Okay, so very nicely explains it, but we need to follow from the beginning, because he talks about basis, rank, and all that. We'll cover rank, but not basis in coming classes. If you are interested, right, you can go there. So this is called as normal equation. Okay. So how exactly it works? Let us see. All your input is like this: row 1, row 2, row 3, and so on. Mth row. In our employee dataset, there are 32 records, 32 rows, and you can take, the designation, the degree, right? All these features: designation, experience, average behavior, activity score, lines of code, all these things as x, right? X1 till xn, and salary as y. Y also has got 1 to m. When you substitute these two, right, these values and these values into this equation, the dimensionality of this matrix is m by n plus 1. Why n plus 1? Why n plus 1?
Index column?
No, x0, the bias term, right? 1 for every row.
Okay.
And we wanted theta 0, that's where we added x0. If you don't want theta 0, right, you eliminate this x0, it's going to be m by n. Okay, m rows and n columns. And no, this bias term is needed because this theta 0, if you need theta 0 in the equation, we have to add that. Rather, it will not come. I told you in the beginning, right? If you want to have theta 0, you should definitely add bias term because of this equation. Not only this equation, even going forward, forward also, in the normal the gradient descent algorithm also, we actually need to add this to get the theta 0. If you don't add it, you will not get theta 0. Okay, so the dimensionality is m by n. So x transpose x, right? If you transpose this matrix, how do the dimensionality becomes? This dimensionality becomes how? When you transpose x.
N plus 1 into m.
N plus 1 by m, right? N plus 1 by m, right? See this n plus 1 by m, right? How the dimensionality, after multiplying these two matrices, what is happening? What is the ultimate dimensionality? I am actually trying to explain. Ultimate dimensionality we expect is n plus 1 by 1, which is nothing but thetas. Okay, so the transpose of x is n plus 1 by m. X is m by n plus 1. We can multiply these two matrices. Right? We are multiplying x with itself. In many places we do. Give me one second. Right, Sridham. Door. So we are multiplying the matrix with itself. Right? This operation we do many times in AI. Okay, this operation we do many times in AI. Multiply a matrix with itself is always done like this: x transpose x or x transpose. Okay, so we can multiply because m are matching. So number of rows in the number of columns in the first matrix should be equal to number of rows in the second matrix. Then only you will be able to multiply. Right? M by n matrix and n by p matrix. When you multiply, you get a m by p matrix. Right? So when you multiply these two matrices, you will get a matrix with dimensionality n by n plus 1 by n plus 1. I am talking about dimensionality only, not numbers. Right? Outcome I am not talking. Okay. So n plus 1 by n plus 1, right? And then x transpose again. Right? The whole inverse we did, but inverse will also have the same dimensionality as we have seen. 1 by AD minus BC, D minus B minus CA, right? See here, the dimensionality of the original matrix is 2 by 2. Inverse is also 2 by 2, right? So when you do x transpose x whole inverse, x transpose x is n plus 1 by n plus 1. When you inverse also, you get the same dimensionality. Okay, no questions there. So x transpose is n plus 1 by m. Y is m by 1. Why m by 1? M number of rows we have. Each row will have one value only. The target variable, salary, 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 like that. So when you multiply these two, it will be n plus 1 by 1. So the dimensionalities are matching again to multiply. So why am I actually highlighting this and showing this is, in deep learning, when you are doing the operations, sometimes you get dimensionality did not match while multiplying matrices. So you need to be aware of this concept, right? This is not just to explain you normal equation. This is just to explain you how machine learning uses linear algebra. Okay, if any time when you are doing deep learning algorithm, you get dimensionality is not matching. Sometimes somewhere you did some mistake and you got m and m not matching, right? M and m while multiplying matrices, m and m not matching. That point you need to remember. Okay, so n plus 1 by n plus 1 and n plus 1 by 1, you multiply these, you get n plus 1 by 1. What is this n plus 1 by n? 1 is all thetas. Okay, that's how the normal equation actually does the operations, and you get this thetas. Got it? Any questions here? Confusions? Questions, confusions? This normal equation itself is not a big thing, but the linear algebra, the matrix multiplications is the thing we use throughout the AA career. Okay. Concept is more important than the equations and remembering the equations and all that. No questions, right? Can I move on?
Yes, sir.
Okay, I think I need to take out these. These are unnecessarily here. Okay, I'll do that. So the problem with normal equation is, right? Let me ask a question. So you have this equation, right? I'm trying to find thetas. Why am I trying to find thetas? The first example you need to remember. There is a house with 1000 SFT. The price is 1 million. There is a house with 2000 SFT. The price is 2 million. The price of a house is 3000 SFT. The price is 3 million. Can you find 4000 SFT price, you immediately said 4 million. Why? Because the price is equal to SFT area into 1000. By looking at the train data, 1000, 2000, 3000 SFT houses, you figured out the equation, the coefficient that multiplies the input feature. What is the input feature? What was the input feature there? What was the input feature in the 1000 SFT example?
SFT area.
SFT area, right? So 1000 into SFT area is the equation you found. That coefficient is what you need to find. Our mind generally calculates that coefficient. Even the machine learning also calculates the coefficient only, right? In a complex setup like this, there are n number of features in our in our setup, simple setup, right? Only one input feature, one output feature. Simply we were able to find out the coefficient. But in a complex setup like this, n number of features, you need mathematics, you need linear algebra to find out coefficients for each of the feature, right? X1 is SFT, X2 is something, X3 is something, Xn is something else, right? We added all these features. That's where we need, this many coefficients, and when you substitute the values into this, we found the coefficients. Okay, so why, that's where we are finding this, that's where the importance of the equation. Yeah, any questions?
Sir, is there any limit for M or N?
No limit. That's the question I'm going to ask now, right? If you have 1 million records in this and 10,000 columns, right, then what happens to the matrix? That whole calculation. First question is, where this whole calculation is happening? X transpose X whole inverse X transpose Y. Where is it happening? In RAM or hard disk?
RAM. RAM.
RAM, right? So if you have 1 million values, let me take a calculator. If you have 1 million values, 1 million rows, and then 10,000 columns, right? 10,000 columns. So that many numbers you have in your data set. Okay. Suppose that each value is a float 64. Right? Each value, each cell, this many values are there in the data set. Right? 1 million rows and 10,000 columns. This many numbers are there. This many cells are there in the data set. This many cells are there in this data set. Now each value is a 64-bit value, right? Into 64-bit means how many bytes? 8 bytes, right? Right? 8 bytes. That much memory it is going to occupy. If I want to convert it into KB, 1 divided by million into 10,000, 8, right? Divided by 1024 is the KB. Divided by 1024 is MB, right? Divided by 1024 is GB. 74 GB it's going to occupy. This matrix itself, right? This matrix itself, if you have 1 million records and 10,000 columns, it's going to occupy 74 GB in your RAM. And then you need to actually do the manipulations, right? X transpose X manipulation you have to do. Even if you use swap memory, your system will not work and it will say out of memory error. Got it? So in deep learning, right, we'll see out of memory errors quite often. May not be in machine learning, we will not see that quite often, but in deep learning we'll see. And if you use bigger data sets, right, you will see that in machine learning also. So I think you can understand machine learning algorithms limitations now. All machine learning algorithms like this way only work like this way only. Okay, did you understood the problem with the normal equation? Will it be able to handle huge volumes of data? Will it be able to handle huge volumes of data? Yes, no?
It's difficult. We need to have extremely high RAM. It's not.
Yeah, extremely high RAM. Maybe supercomputer we need to have. Right? There is solution. right? This is one big problem that linear algebra, linear regression algorithm has. To avoid this problem, we will be going into another algorithm called as gradient descent. We call that a solver, not an algorithm. For linear regression algorithm, normal equation is one solver, gradient descent algorithm is another solver, which actually, no, not gradient descent, but stochastic gradient descent algorithm, which actually takes one record at a time. And 1 million records it actually calculates cumulatively. Theta it gets improved cumulatively, or theta learned cumulatively. First record it learns something, second record it learns even more, it's a third more, fourth more, like that. Okay, that is stochastic gradient descent. So to understand stochastic gradient descent, we need to understand gradient descent algorithm. Okay, so algorithm has got algorithm, or the solver has got difficulty or incapabilities to handle huge volumes of data. So now we are going to learn an algorithm which can handle huge volumes of data. Okay, that is one problem with the normal equation, right? Pros with normal equation is no features are scaling needed, no iterations. So in this approach, right, you take the data, you substitute into equation, no pre-processing is done. The feature scaling and iterations we see in gradient descent algorithm, I'll explain that. In those algorithms, right, we need to do these explicitly, rather the algorithm will not work perfectly. But in normal equation, right, it is not needed. You take the data, you take y, you just substitute into it, you get the thetas. But on a small data set it works well. Okay, big data it will not work well. So the problems, cons with it, x transpose x whole inverse is computationally expensive. Okay, when we have too many features or columns, right, then computation will be very slow. And one more thing is, one more problem with this normal equation is, if you have 10 rows and 20 columns, the algorithm will not work. Okay, if you have 10 rows and 20 columns, the algorithm will not work. Why? You have 10 rows in the data set and 20 columns in the data set, right? The algorithm will not work. Why? Do you know? It's a simple linear algebra concept.
Matrix multiplication.
Rows and columns should be matched.
Sorry, Andy. Sorry.
Rows and columns should be matched, equal, right?
Rows and columns must be equal, or columns must be less than rows. Because what are we trying to find? Thetas, right? If there are 3 columns and 10 rows, the equations are going to be theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. Right? What is x1, x2, x3? Values in the data. Right? When you form equations, right, you get 10 equations. I hope you are understanding all my statements. If you don't understand one of them, just stop me. Okay. So you have 3 columns. Your equation, the hypothesis function is going to be theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. When you substitute your input values, the data values, into the equation, it is going to be theta 0 into this value, theta 1 into this value, theta 2 into this value is equal to this value. Theta 0 into this value, theta 1 into this value, theta 2, theta 3 into this value is equal to this value. Like that, it's going to form equations. So when you are actually forming equations, there are 4 unknowns. What are the unknowns? There are 4 unknowns. What are the unknowns here?
Theta 1, theta 2.
Theta 0 to theta 4.
Yes, sir. Good, sir. Thank you. So I'm just checking whether you are following or not. So theta 0, theta 1, theta 2, and so on, theta n are the unknowns. The unknowns must be less than the number of equations, less than or equal to number of equations. Then only you will be able to solve the equations. That's one of the linear algebra concepts. Okay. So if you have 20 columns and 10 rows, your unknowns are 21 and your equations are 10. So you will not be able to solve the equation. Or when you try to solve the equation, right, you get a singular matrix. Okay. When you do x transpose x here, you get a singular matrix. When you get singular matrix, you will not be able to find inverse. When there is no inverse, right, this whole equation will not find thetas. There is a concept called a pseudo inverse. Okay. but I'm not going to go into those details, but no need to learn also. So linear regression algorithm works even when number of columns are more than number of rows using pseudo inverse. When it is unable to find inverse here, it will use pseudo inverse and do it, but it is not the right way. Okay. So X transpose X is computationally expensive. Yeah, please.
1 second. So you mentioned that when there are more number of columns than number of rows. Okay, so in that case, the number of equations will be less than the number of unknowns. That's what you said, sir. Correct?
Yeah, number of thetas.
Okay. Sure.
Right?
Okay.
Number of.
Yeah. Okay, sir.
So my problem here is I'm in hometown. I don't have a table. I cannot put my that pen thing, right, the tablet. That's where I'm actually speaking. So I hope you got it, right?
Yeah. So maybe if I'm not very sure about others, if you had
Others,
drawn,
yes.
if you had drawn a picture like
Yeah.
something like that, right? So
Maybe
where
let
we
me
can
try
see.
that. Let me try that. Give me 1 second. Try to draw this and explain. So let me. So what I'm trying to say is if you have x1, x2, x3 and y, right? And then there are 10 rows, right? Row 1, row 2 and so on, row 10. Now we have more rows than number of columns, right? Number of rows are more than number of columns. Now if you pass this to linear regression algorithm, right? Linear regression algorithm, what it will do is, what is the hypothesis function of linear regression algorithm? It is theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 is equal to y, right? So maybe I'll put some values also here, right? Now here theta 0 I am putting, so x0 will come. X0 is always 1 for every row. The x0 value is 1 only. That is called as bias term. Okay. So when you pass this to linear regression, what it does is it forms the equations and solves all of them at once, right? How is it solving all of them at once? That whole concept is happening with the normal equation. Okay. Forming the equations and solving all of them is happening in a single chart. Theta is equal to x transpose x whole inverse x transpose y. Right? These values will go here. These values, right? These x values, right, will go here into this set. Right? You get all thetas in single chart. But the concept I was trying to explain is number of rows must be greater than number of columns to make this normal equation work for best. Why? Because when number of columns are more than number of rows, x transpose x is going to create a singular matrix. X transpose x is going to create a singular matrix where the whole multiplication, this whole thing, the outcome of this x transpose x will not have inverse. Okay. So when the point I was trying to explain is, if you pass this data to linear algebra, linear regression, what happens? It actually going to form theta 0 into 1 plus theta 1 into, maybe there is 10, maybe I'll take some values, 20 is equal to maybe 55, 15, 6, maybe 21 is equal to 26, like that. Okay, maybe I'll put 10, 5, 15 is equal to maybe 15, like that, right? If data is like that, so what happens? The unknowns we are trying to find are the coefficients in our SFT area example. SFT and the price 1000, 1 million, 2000, 2 million, 3000, 3 million, right? As soon as we looked at this data, we understood that price is equal to 1000 into SFT, right? This is the unknown we found. If we don't know this, right? No, right away I'm putting it like that. If I don't put it like that, right, I would have formed the equations like this. The theta 1 into 1000 is equal to 1 million. Theta 1 into 2000 is equal to 2 million. But I am not putting zeros correctly, but take it. Theta 1 into 3000 is equal to 3 million. Like this, I would have formed equations when I passed it to linear regression. I would have formed these equations and then solved these equations to find this unknown. Okay, like that. If you have more columns, right? What I'll do? I'll actually form equations like this: theta 1 into 10 plus theta 2 into 5 plus theta 3 into 20 is equal to 55. Right? Theta 0 plus into 1 plus theta 1 into 15 plus theta 2 into 6 plus theta 3 into 21 is equal to 26. Like that, I will form the equations and solve them. Now, maybe if you want to solve individually, right, you would have solved these two, these two, these two, these two. Again, like this equation, that equation, this equation. Like that, you would have done a Cartesian product and solved all equations, found the thetas and found an average of all the thetas and used that as the linear regression algorithm's coefficients. Got it? Got it? Got it? Any questions there?
Yes, sir.
Right?
Yes, sir.
So now the point I was trying to explain is these number of columns must be less than number of rows. If they are more, right? There are 10 rows. If you have 20 columns, x20, right? And so on, x20. What happens? The unknowns, right? Thetas are more than number of equations. So when thetas are more than the point is, right, when you solve two equations, you will get one unknown. When you solve two more equations, you will get one more unknown. When you solve two more equations, you will get one more unknown. Like that, it will happen. By solving 10 equations, you will get 10 unknowns. Rest of the 10 unknowns will be unknowns only, right? You will not be able to find them. Number of columns must be less than number of rows for normal equation based linear regression algorithm. Normal equation based linear regression algorithm can be executed with different solvers. Normal equation is one solver. An algorithm which depends on normal equation should have less number of columns compared to less number of rows. Okay, must have. Okay, so if not, what happens? This x transpose x will give you a singular matrix. This whole multiplication will give you a singular matrix which will not have inverse, and this whole theta calculation business actually gets screwed up. Okay, so that is one problem. Another problem with the normal equation. First problem is memory, right? When data is too huge, right, as we have seen, 74 GB of RAM you need, right? 74 GB of RAM, you will not have a normal machines. Maybe you need to take a cloud computer or maybe go to a supercomputer, right? So huge volumes of data. The linear regression algorithm based out of normal equation cannot work. I am actually talking in a different way now. Linear regression algorithm based out of normal equation solver. Why am I talking like this? Tomorrow I am going to introduce you to linear regression algorithm which works based on gradient, stochastic gradient descent. Maybe tomorrow, day after tomorrow. Okay, so that will work on a huge volume of data. Okay, so that is one point, right? One concept, and one issue with the data. See this here: n greater than m, number of columns greater than number of rows, right? So non-invertible. There are two cases where you get non-invertible x transpose x. What is x transpose x? It's a multiplication. That multiplication is going to be a matrix. That matrix is going to be non-invertible when n greater than m. The second point is dummy variable trap, right? When I was creating get dummies, right? Did you see that get dummies method? Did I show you how to create one hot
Yes,
variables
one
in
heart code. Yeah,
Yeah, one hot
one,
encode.
one
one
hot
heart
encode?
is the term. Yeah.
Get dummies, I said ignore first true, right? If you don't ignore first true, what happens is it will create a strongly correlated column. When your data has got strongly positive correlation or strong negative correlation, right? Then also the X transpose X creates a singular matrix. Okay. The example I will take generally is, let me try to take an example and explain. Let me try to move this upward. So if you have a data set like this, maybe exit polls data, right? Exit polls data, whether the person is going to vote or not is the prediction, right? Age of the person, gender, okay, and then locality, city, some data, right? The y variable is going to be vote or not, okay. So this is the data set. Suppose that this is the data set. You have the train set and you need to build a model. When a new person's record comes in, you are going to pass it to the algorithm model, right? And then that will predict whether the person is going to vote or not. Okay, so that is the problem. So in this gender, we have got male and female, male, female, female, male, like that. There are many records. Okay, so now should we be doing gender column one hot encoding or label encoding? Can somebody answer? Gender column, should we be doing a one hot encoding or label?
Label.
Why label?
There are only two values, right? We can.
Yeah, that's one proof that I'd say that's one way of answering it, but I we can think a
No,
little more.
I think we go for the one-hearted coding because
Why?
0 and 1.
Why 0 and 1?
Because
Why
see,
one hot?
whenever there is a if you are go for the course, uh, it is a ordering problem. It will give the ordering problem one, ranking
Ah,
problem.
why not ranking? Why shouldn't we give rank to male and female? Should I give male high number, female low number, female high number,
No,
male low number?
the one-heart code, one of the advantages, if there is a two categories in the gender,
Ah.
we can give the one value, so not required for the other one.
Let me take transgender also. Three columns, three categories are there. Now, now what should we
Now
do?
it is one hot.
One-
Why one heart? Why one heart? Why not label? Why not label them? Why not label and coding? What is the problem we are trying to solve? If you look at the problem we are trying to solve, we will get an answer whether to go with one heart or label. Person is going to vote or not, right? That's the problem we are trying to solve, right? Right?
Yes, yes.
Is there any hierarchy? Male vote counts high, female vote counts low, or transgender vote counts even lower?
No.
We can't say on male and female, but transgender generally less.
No. When somebody is voting, right? Male vote has got 10 points, female vote has got 20 points, and
No,
transgender
no,
has
no,
got 15 points.
no.
Anything like that? Each vote
No.
counts only one, right? In that case, we should be going with. I would say one thing: we should remove. Actually, this column is not needed. Do you agree with that statement?
Yeah.
Huh?
Yes, yes,
Yes,
yes.
because the weightage is same for all.
Yeah, same for all. We can actually remove this. But I took this example to explain you. It depends on the problem we are trying to solve. Whether we should go with one hot encoding or label encoding. Whether there is a strong relationship of each category to the target variable, then you go with label encoding because you will assign rank to each of the category, right? When you say one is higher than low, when you are giving numbers, you are saying one is higher than low. One category is higher than other category or lower than other category. That is label encoding. When you are not giving any number, right? Every category is getting 1. Rest all are getting 0. That means you leave the decision to the target, the decision to the algorithm to make whether to use the category or not. That is one hot encoding. Here we can actually remove the column. In this particular example, we can actually remove the column. But for understanding purposes or explanation purposes, I am taking it as a one hot encoded column. Okay, so I am eliminating the transgender here because I wanted to explain this dummy variable trap concept here, right? So suppose that there is male and female only, and you all agree that we can go with one hot encoding, right? When you do one hot encoding, how the data set will get converted to, how this data set will get converted to?
Add two more rows.
Two more
Sorry,
columns.
columns. Sorry, columns.
Fine, sir. Fine, sir. Fine, sir. Your intention is right, or you understood it right. So G underscore M and G underscore F are the gender male and female columns. Okay, and then locality, city, right? This is how the data set actually gets converted. This is what I said when I explain one concept, right? I'm going to use it again and again, and you will get clarity, right? I think you should have got more clarity now. Even if not, let me know. I'll actually go over it again, right? Now what happens? Some value here, but if the record belongs to first record belongs to male, so I'll have 1 here. I'll have 0. Some value. We don't care, right? Second, right? This record belongs to female, so this is 1, right? Actually, we can remove in this particular scenario. We can remove, but for understanding purposes, I am using it. Okay, like that, the data set will become like that, right? Now, if you look at the gender male and gender female, right? Are they strongly correlated? Are they strongly correlated? If yes, what
Yes,
is the correlation? What is the correlation? Is that positive or negative?
inverse, negative correlation.
Negative correlation, right? When you try to calculate the correlation between these two columns, you will get -1. Right? If you have this kind of data in your data set and you are trying to use linear regression algorithm, right? Linear regression based out of a normal equation solver. Normal equation solver. If you are using gradient descent, right, you will not have this problem. Normal equation solver will create a singular X transpose X matrix. This X transpose X is going to be singular. Now, when you say inverse, right, it will not be able to find out the inverse. This is the reason why I said drop first is equal to true. If I drop this column, right, if I drop this column while creating dummy variables, if I drop the first column, I am eliminating the possibility of getting a strongly correlated column or inducing strongly correlated column into the data set. That it drop first true will actually eliminate the inducing strong correlation column into the data set. Did you get the point? Did you get the point? Can I move on?
No, sir. Please go on.
No.
No.
So if I don't, so there is in pandas, right? There is a method called as get dummies, right? And you pass the categorical column, right? And the categories it need to be. So it will create these columns, right? That point you know, right? This method, and which actually creates these columns. You know that, right? Yes, no,
Yes, sir.
right? In this method itself, you have another parameter called as drop first true. Drop first is equal to true. If I say that it is going to eliminate this column. If you have two categories, when you create dummy variables, you got two columns. If you have three categories, right, transgender is also there, you would have got three columns. But when you say drop first is equal to true, it is going to eliminate the one column and take the two. Right? This will actually eliminate the strongly correlation. Right? This is a simple example which actually says male, female, both you create dummy variables, you will get a strongly correlated column, and this X transpose X will fail, and the equation generated may not be right. So that that drop first true, we said, we eliminated this model will work now, this algorithm will work perfectly now. But is this representing the data? If I say 0, female 0, that means male. If I say female 1, that means female only, right? This is actually sufficient. One column is sufficient. No need to create two dummy columns. One dummy column is sufficient to represent two categories. If I have three categories, if both are 0, suppose that transgender is also there, G underscore T is also there, right? Then what happens? If here also 0, that means it is male, right? Got it? Both are 0, that means it is male. Got it? The record belongs to male. Even if you eliminate one column, you can represent your categories. That's what I am trying to explain. And you will be eliminating the dummy variable trap. This is called as dummy variable trap. When you create n number of columns for n categories, you create dummy variable trap where the normal equation will fail to work. Got it?
So by removing that, that extra column or dummy variable, you are saying that the model will perform better.
Yeah. You are not convinced.
Yeah, when we have taken the transgender, right? So
Even when you take transgender, we can eliminate the one first column.
Yeah, that elimination part, yes, I understand. But how is it going to improve the model? Just
See, the problem with the normal equation is when there are strongly correlated columns, X transpose X will become a singular matrix. Okay? That is the problem. That is the base problem. To solve that problem, what we need to do? We need to make sure that there are no strongly correlated columns in the data. Okay? When you took the original data, there is no strong correlation columns. But when you created dummy variables, you may be inducing the strongly correlated columns. To eliminate that problem, we are saying drop first true.
yeah. Maybe if we extend this, let's say we are considering only gender. Let's say there is other input variable similar to this, which has 4 or 5 distinct values. When we say drop first, will it drop first from all those dummies, or it drops only?
Every column, right? Gender is there, and then maybe designation is also there, right?
Okay.
Right? For vote designation is not needed, but I am taking example as designation. Designation also you are trying to convert it to dummy variables or the one hot encoding. Right? There also you say drop first true. While creating that particular one hot encoding for the designation, you are making sure that no strong correlation is generated. While creating gender column, you are making sure that no strong correlation is created. But unfortunately, you may get one column from here and one column from there also get strongly correlated. Maybe that's what your question is, right?
No. If we have multiple categorical columns, and when we generate the one hot encoding columns, then when we provide this drop first, will it drops for one hot encoded column from each category?
Yes, that's true. That will actually make sure that the normal equation will not get into dummy variable trap. What is dummy variable trap? X transpose X becoming singular matrix is the dummy variable. Okay.
Yes, sir. I mean, we'll move forward, but I'm just a bit
think
confused with this X transpose becoming singular. I'm just need to spend some time.
Yeah, maybe linear algebra it is, right? So
Yeah.
linear algebra theoretically proven concept it is. If you have time, right, you can actually look into it.
Yes, sir. Yes.
So
Yes,
no
sir,
dummy.
just to
Yeah, please.
summarize, basically we are removing one column and another column we are trying to represent the removed column together as a alternative. That's how we are trying to still solve the problem. Is that correct, sir?
Yes, yes, sir, yes, sir.
That's what basically in summarized way. If I have
Yes.
10 categories, one hot encoding will create 10 columns, but we don't want to, because that will create the dummy variable problem. Trap, we are trying to make it 9, that is 10 minus
Yes.
1, and in maybe a ninth column, or just an example, I am trying to represent the removed column together somehow.
If all 9 columns have zeros, that means 10th column is the
Exactly.
the record belongs to.
Exactly. Okay, clear, sir.
So there is another example I have given. Employee experience in years and employee experience in months. You have 2 columns, right? They are strongly correlated. In that case, you will get a singular matrix. When X has linear dependent features, X has linear dependent features. This is a linear algebraic terminology. Linearly dependent feature means you take one column and you multiply with some number, you can generate another column. If you see this, years of experience in years and months, you multiply something or divide months with 12, you get this column, right? So you multiply this with 12, you get this column. So they are called as linearly dependent columns. When X has linearly dependent columns, X transpose X will generate singular matrix. A singular matrix has no inverse as determinant is 0. So removing redundant features or apply regularization will actually solve this problem. Regularization we still not seen, right? Regularization will get in the gradient descent algorithm. The one solution is gradient descent algorithm only. Okay, so that is normal equation. And how is it actually solving the what you call it as the linear regression algorithm is working and all that. So I would stop it here and then jump back to, I think I did not show you one complete example on how to use the statistics and inferential statistics and all while building a model. Okay, any questions so far? Are we good? I'll take maybe 10 more minutes of class and then I'll stop today. Any questions? Good. So this 16th file, I don't know whether I uploaded it or not. Right? This is actually the complete EDA and then model building activity. Okay, we know the data set, right? We splitted the data. We found the best values to impute. Okay, and then we know how to actually convert categorical column to numerical. And we were collecting all the categories available in each of the column, right? And then calling that method whatever the category. But on the train set I imputed values here. But whether these categorical columns, should I be converting them to category the one hot or label, right? That's what we need to find. We can actually do the cat plot, which actually shows you the averages of different categories, right? Here I took designations in X and salaries on Y. So the average salary for this designation, average salary for this averages are different. That means the designation, that particular columns categories are distinct in their nature. So we can do labeler coding. Okay. So by looking at this graph, you can understand. But we can do a box plot, which actually shows outliers also. See, we are trying to consolidate everything, whatever we have learned so far, on the the synthetic salary prediction data set. Okay, so box plot, salary is the Y value by designation. So you do the box whisker plot by each designation. So it is going to group the data by designation: analyst group, directors group, junior developers group, managers group, senior managers group, like that. It is going to group the data and take the salaries and find out the box whisker plot. All analyst salaries, box whisker. All director salaries, box whisker. What is happening here? It is actually trying to show median, maximum, minimum, right? All that stuff. You see this graph? What do you call these dots as? In this or this?
We can say outliers after the minimum or after the
Yeah,
maximum.
outliers, right? So these are outliers. But is that really true? Yes, it is. For some junior developers, even though the experience is less, industry pays high. Okay, so this is real. This is real data. You should not be removing it. But if you are looking at millions of records, right, then this will be more useful. This graph will be more useful. Okay, so by looking at this data, these graphs also, we can see that there is distinction between each designation and the other designation salary. So we can go with label encoding. Okay, but still I did multi comparison. The what do you call it, ANOVA test. See this, most of the five pairs said reject true. Only one said reject false. But one or two, like maybe 5, 6, that doesn't matter. So we went to label encoding. Okay, convert categories to codes. Okay, that is label encoding. Okay, and then gender and salary. Okay, I am trying to look whether there is distinction. There is not much distinction. We can actually go with one hot encoding. See, I did one hot encoding. So there are only two categories here in the gender column. So I did one hot encoding using OLS algorithm. Okay, so oh, I did categorical here. I don't know. I can do. Maybe I looked into this reject null hypothesis where. Oh, okay. So when I did this OLS algorithm, right, I found that reject true. Right, they are independent. They are dependent. I got male salary is greater than female salary or something like that. That's where I went to one hot encoding. Sorry, label encoding. Okay, and then the salary, then the qualification and salary. Again, I did the plots and multi comparison. 3 said false, 3 said true. We don't know which direction to go, so we went into one hot encoding. We know that the direction we will go to label encoding. If you don't know, we will go to one hot encoding. And then I don't know what is this column. Degree. Right? Everything said false. And only 2 said true. I think we can remove this column basically. Because most of it is saying reject, false. Right? There is no dependency. There is not much impact of designation on salary. We can remove this column basically. But I kept it and I think I dropped it. See this, I dropped it. Okay, and then educational institution, here also, here and there. So we went into, see the get dummies. This is a dummy variable creation, one hot encoding. So to get dummies, I pass the data set, I pass it the column, I pass the prefix and drop first true. There are maybe four educational institutions. I created only 3 columns because I said drop first true. Right, prefix, right, for that particular column, column name and then the category. It is going to create the dummy variables. And then look at the file and you will understand, right, all these columns. Now the data is ready. See, I took the data set with some number of columns and after adding dummy variables, the number of columns got increased and the X and the Y, and I splitted the data. I took the grid set CV, passed 1, 2, 3 degrees of whatever that polynomial and built a model. I got 98% accuracy. I'm actually doing all the pre-processing, right? Whatever the conversions I did, the categorical columns to numerical columns. you can build a custom transformer to eliminate this much of code. You just call custom transformer the pipeline dot or the grid set cv dot predict. It will actually automatically apply all these and then calculate. Yesterday I explained you custom transformer. See this on the trains at test set, it is giving less accuracy. We went theoretically and tried to build it, and it is not working well because of data size. It is working weirdly. But if you have huge volume of data, you would have got better insights when you did the hypothesis testing. We would have done proper conversion of categorical columns to numerical, and the model would have worked better. Because of only 32 records or maybe 1500 records, the model is not working well on test set. It looks like it is war fitted. Okay, but when data is huge, right, it will work. It's a toy data set, so no, it is acting weird. Did you get it? Any questions here?
Yes, sir. So we are doing all these things whether to decide whether two columns are a sum of the columns, or we need to do whether one hot encoding or label encoding. All these things we are trying to see by plotting this one.
Yeah,
So
visually as well as statistically.
yeah, exactly. So without we doing it, you are saying that there is a algorithms can take care of that. Is that what you're saying, sir?
We have to. This is all we have to do.
Okay.
Linear regression algorithm will not do anything. This is all we have to do, and we need to. I made this decision of converting a particular column to one hot encoding, a particular column to label encoding by looking at statistics.
Okay. So is there no algorithm which will take which does all these things in the background and
there are approaches, regularization and all that stuff will actually do it, and deep learning will also do it. But as a data scientist, we should be taking care of it a little bit.
Sure.
Right? How good the data is, that good the pattern recognition is going to be. Algorithms can do, but their job they'll do perfectly. But our job also we should do perfectly.
Okay.
Before we hand over the task to a machine learning algorithm, whatever is in our hand, we should be doing it.
Yeah.
Yeah,
maybe as an
without that, right? If algorithm can handle everything, right, we would not have learned all this, right? It's a waste of time, 1.5 months of waste of time, right? We have to, we must do this before we pass the data to the algorithm. How good you transform data, how good you transform your data and represent in the business essence in numbers, that good the model will work.
Yeah, sure.
Yeah. So, like, we know that a particular algorithm is capable of converting this into one hot or label. Still we have to do in some cases.
No, the algorithms will not convert data into one hot or label. Algorithms will see how good the feature is, how bad the feature is. Based on that, it will try to assign coefficients. Okay, it will not do one hot and label. I think Girigar question was that, is there any algorithm that actually does automatic conversion? No, there is no algorithm that does it. Okay, but if you pass your data, suppose that you converted all columns to label encoding, passed your data to the model, it will see how strongly it is affecting the target variable, how weak it is affecting the target variable. Based on that, it will actually find out the coefficient. That's it. That coefficient finding will actually happen automatically, and it will give good results many of the times. Okay, got it?
Okay, so
Yes.
the label encoding or the one hot encoding we have to do manually
Yes.
for anything. Okay.
Yes. On huge data sets, we will not do it. We will see that. No, don't
Okay.
get confused. Once after regularization, right, you will get more clarity.
Yeah.
Gradient descent, stochastic gradient descent, and regularization concepts, once you understand it, you will get a complete clarity on how machine learning algorithms work. What are their capabilities? What are their weaknesses? Why do we need to do all this, tedious job of converting the data into numbers? Whole NLP is about that. The unstructured data, natural language, you need to convert it into a appropriate format. That's where the whole NLP is all about. Machine learning algorithms are there, deep learning algorithms are there. We need to convert text data into numbers, appropriate numbers, not losing essence. Right? That's what we need to make sure. Okay.
Sir, I have one more simple question. Just can you please go up a bit? So this multi-comparison result, I think, come down please. Yeah. So this table, when I applied the multi-comparison, the statistical test. So when I applied this two-case honesty test for Melbourne housing, so I'm getting a lot of maybe around 50 or 60,000 records here. So it is a bit tough for me to check whether truths are more or falses are more. So this is actually a stats model simple table.
On which column? On which column you are doing this?
It's actually region, suburb, sorry.
Suburb, okay. Suburb, suburb, I think by looking at graph, you should make the decision. If the graph is zigzag, right? You can actually go for label encoding. But business actually explains you, right? Suburb will have importance, right? So you can go with
Suburb.
label encoding. No need to do multi-comparison. For all columns, no need to do it. If you know business, right, you can make a decision. If you don't know business, then you take the help of these statistics. Got it?
Okay, so the suburb is strongly related to the
Price.
price prediction. So we have to, by default, we have to consider it as label encoding.
Label, yes.
Okay. So how the value will be assigned? Okay, I think we have discussed random assignment, right?
Yeah, random assignment, or you can assign your own using some logic. But you should remember, you should
Yeah,
have
the
a
same
dictionary.
value should be
Yeah,
applied.
same.
Yeah. Okay. So out of my curiosity, is there a way to find like the counts of reject true or reject false? This is the stats model
I
simple
think
table.
I think I think if you look at the structure, right, the type of the object here, if it is a data frame, you can take that particular column and do it. I don't know. I never looked at the
It
type
is
of this
actually
object.
stats model simple table object
You
type.
need to look into that API and see how the structure and or maybe you need to convert this into data frame and then you should be looking like that. I never
Yeah.
did that. On that kind of data, right? You generally not try to do one hot encoding because if you do one hot encoding, right, it'll add many columns in the data. In
Yeah.
that category, right? In that case, what you will do is you will try to find buckets, right?
Okay.
For each of the category, if you have maybe 1,000 categories, maybe 100 categories fell into one bucket. Bucket in the sense average target variable value is kind of near to each other, right? And then the maybe 50 falling into another bucket, 50 falling into other, like that you make the total thing into 5 6 buckets, and then try to assign the label or one heart.
Okay.
Okay.
Yes, sir.
So ultimately, the ultimate uh, understanding or the result is that we need to represent data in numbers that will not lose essence in business. Okay, whatever business is saying, the number should also represent almost close to what the business is saying. That should not get lost. Data pre-processing should not damage the business essence. That's the care we should be taking. Got it?
Yes, sir.
Whatever you do is right until and you take care of this one point. Right? Business essence should not be lost while converting your data to numbers.